Now let's take a closer look at unbounded behavior. Another reason a limit could fail to exist. And so in this picture, in this graph, we saw that f of x is increasing without bound as x approaches 0 from either side. A limit in which f of x increases or decreases without bound as x approaches a, we call that thing an infinite limit. And we got one for increasing and one for decreasing. And this is the notation here. The limit as x approaches a of f of x is equal to infinity. That means it increases without bound. And then we have the limit as x approaches a of f of x is equal to negative infinity. It decreases without bound. Now, this is an important note here. This doesn't mean that these individual limits exist because I put the little equal sign, and we're not saying that it's actually a number that is equal to infinity because that's impossible. This is just convenient notation to indicate that this limit does not exist due to unbounded behavior, but it does a little something extra. It tells us what direction that graph is going. This one's going upwards, it's increasing without bound, and this one's going downwards, decreasing without bound. Look at the pictures over here. What the heck are these pink lines that are right here? Those on a graph are asymptotes, and so we can use limits, either one-sided limits or not, to describe what's happening to the graph around those vertical asymptotes, either increasing or decreasing without bound. We can do the same thing with horizontal asymptotes, and we'll see that in another lesson. But here, the vertical line x equals a is a vertical asymptote of the graph of y equals f of x if at least one of these statements is true. So we've got 4 different things that could possibly happen, either on the left side or the right side, either increasing or decreasing without bound. So you can see these written as one-sided limits. The limit as x approaches a from the left of f of x is equal to infinity. On the left side, it's increasing without bound. We can do the same thing on the right side. It can increase without bound. Or we can decrease without bound on the left side, or we can decrease without bound on the right side. The limit as x approaches a from the right, f of x, is equal to negative infinity. So speaking of vertical asymptotes, let's take a look at example 7. We want to evaluate each of these following limits, and you can see that they're all one-sided limits. So on this particular question, one of the things that I want to suggest to you whenever you're evaluating these limits, and definitely as we move into the next lesson, first thing you want to do is just plug in that x value. So if we plug in that x value here, let's see what happens with this thing. There's nothing that we can do up top. It's always going to be a 1. But when I stick negative 1 into the bottom, doesn't matter if it's on the left side or the right side, I would have a 0 right here. Negative 1 plus 1 would give me 0. Times 2 doesn't even matter. I get 1 over 0. So think about this for a second. If we have any kind of number, not 0, divided by 0, what happens? This is not an indeterminate form where we have ourselves, let's say, a point of discontinuity on the graph. Instead, this is going to be a vertical asymptote, and our graph is going to shoot off to either plus or minus infinity. And so what we want to be able to decide is which one is it? Is it increasing without bound, or is it decreasing without bound? Well, one of the ways that you could do that is just look at a graph. But we don't always have access to a graphing calculator. We don't always want to graph one by hand if we could on some particular examples. So what we're going to do instead is assign, S-I-G-N, a sign analysis. So basically, we just want to know positive or negative, right? We're just going to be able to determine which one this is based on the kinds of numbers that we have. So on this particular one, we want numbers that are less than negative 1. So sometimes it's a little tricky to think about, wrap your head around when we're talking about negative numbers. Here's negative numbers. Well, smaller than negative 1 is over here on the left-hand side. The number itself, though, is actually a bigger number. So it's like negative 1.1. So think of that in your head for right now. And for our sign analysis, the one that's on the top is positive, and it will always remain positive. So we have a plus up top. On the bottom, however, if I think of this pretend value that's close to -1, but just a little bit smaller on the left-hand side, -1.1 plus 1, it's going to leave a negative number down here. It's really small, but it's negative times +2. That whole thing in the bottom is negative. That's a 1. Negative. So positive divided by negative, this whole thing is going to be a negative number, and we will say that it is approaching negative infinity. And that's what I would write for the value of this limit, negative infinity. And remember, that doesn't mean that the limit exists. It means that it does not exist due to unbounded behavior, but specifically that part of the graph is going down. If we have, let's say, a vertical asymptote here, and we were to draw in its graph, this portion of the graph is shooting downwards. Okay, let's look at number 2. The limit as x approaches 1 from the right, we have x squared plus 1 over x squared minus 1. I'm going to do the same kind of thing here. I want to first plug in the number 1 just to see what's happening here. I want to see, does this happen, or do I get that 0 over 0 indeterminate form, which implies that we have a hole that we have to fill. So this one, up top at 1 squared plus 1, I would get a 2. And then on the bottom, 1 squared minus 1, I'd get a 0. So it's the same exact situation, and I want to understand that I'm going to shoot off to either positive or negative infinity, indicating a vertical asymptote here. And we want to just determine which one is it, positive or negative. We'll do that with, again, one of these things called a sign analysis. This time we're a little bit bigger than 1. So I can think again of a number like 1.1. Up top, no matter what, whenever I square my number and I add 1 to it, it'll always be positive. So I have a positive up top. On the bottom, when I take a number that's a little bit bigger than 1, square it, and subtract 1, this side is going to be bigger than that side, and therefore we're left with a positive number. Plus divided by plus gives me a positive infinity. So this time on the graph, this one's going to increase without bound, going to positive infinity. All right, last one, number 3, we have ourselves a trig function. And I don't know about you, but I tend to not think in terms of cotangents. I am, I guess, elitist in that way. I prefer sines and cosines, so I'm going to change it. So limit as x approaches pi from the left, and change this to cosine over sine. So I'm going to do the same thing that I did before and just visualize what's happening if I do plug in the number pi. And in order to do so, maybe what I should do is draw myself a unit circle. Those things come in pretty handy. Oh my God, it's perfect. All right, so here's pi over here. And we are specifically talking about numbers that are less than pi. So less than pi on the unit circle is the top portion here. So let's visualize, say, a point that is up here, right? But regardless, whenever I plug in pi, I would get, up top I would have a -1. That's the x value there, right? Because the point is -1, 0. And the y value for the sign is 0. So I have the same exact scenario here, a number that's not 1 divided by 0. I'm going to make the association that that's going to shoot off to positive or negative infinity, and we're trying to figure out which one it is. So I might think that since I have a negative up top divided by this 0 here, it might go to negative infinity, but it's a good idea to check just to be sure, okay? Because that's not always the case when we have these one-sided limits, as I will show you on a follow-up question to this one in just a moment. Okay, so as we were saying, a number that is a little bit less than pi on the unit circle lives basically in quadrant 2 here. And so think of the xy coordinates for a point over here. It's going to be negative for the x value for the cosine, and it's going to be positive for the sine. So essentially, I have a negative divided by a positive. Negative divided by a positive implies that this thing is going to shoot to negative infinity. So if you were to think of the graph for cotangent, has a vertical asymptote here at the Y-axis, it also has 1 at pi, and then your actual graph looks like this. And then here's pi. And then we can see that this graph is indeed decreasing without bound on the left side of pi. But what if this said the limit as x approaches pi from the right-hand side of cotangent of x? Well, on this one, here, let me actually change colors of everything here so nothing gets confused. Let's see, what color do we want this one to be? What color do we want this one to be? Purple? Okay, I'm with you. So we'll make this one purple. And then this time on, choose my purple crayon, a number that's bigger than pi. This time it's going to be in quadrant 3. And in quadrant 3, my xy coordinates would both be negative. So this time I would have a negative divided by a negative, which is a positive number. Boop, boop. So this one should be shooting to positive infinity. So think about the graph. The next branch of the graph on cotangent, it would be just the same exact kind of thing over and over again. And we can see on the right side of pi, it does shoot up to positive infinity.